This is a walkthrough of a Further Mathematics A-Level Further Mechanics 1 paper. Question 1. A van of mass 750 kg is moving along a straight horizontal road. At the instant when the speed of the van is v meters per second, the resistance to the motion of the van is modelled as a force of magnitude 200 plus v squared newtons. When the engine of the van is working at a constant rate of 12 kilowatts and the van is moving at a constant speed, part A, show that the van must be moving at 20 meters per second. Justify your answer. Well, the first thing I've done is underline all the important things in the question and then converted it into a diagram. It's moving at a constant speed, and I've got it going to the right on my diagram here. The tractive force, well, that's the power over the velocity, and the resistance is going to be 200 plus v squared. Now, since this is moving at a constant speed, it means that the tractive force is going to be equal to the resistive force. So that will be P over V is equal to 200 plus v squared. That's the resistive force. So I'll replace the power with 1200 kilowatts or 12 kilowatts, sorry. So that's going to be 12,000 watts divided by the velocity is equal to 20 plus v squared. If I times both sides by v, take the 1200 across, I will get v cubed plus 200v minus 12,000 is equal to 0. Now, if I put this on my calculator to help me factorize it, from the calculator I get v is equal to 20. So factorizing, that will give me v minus 20 in one bracket. I'll now work out what needs to go in the other bracket. Well, if I've got v cubed, then I need to have v squared in that bracket. And if I've got minus 12,000, then I need to have plus 600 at the end. I just need now to work out what goes in the middle. Now, I want to get 200v in the middle as the term here, coefficient of 200. So I know when I multiply out these first two terms here, I get v cubed. Then I know that the last two terms are going to give me negative 12,000. Now, if I've got v times 600, that gives me 600v, which is too much. I want to take off 400 v's. So that means that I need to put plus 20v here for this all to balance out. And you can check multiplying out the brackets, then this works here. So if I take this part out here and put it on a calculator and try and solve it, it has no real solutions. You basically get complex solutions. So no real solutions here. V has to be real. So that means the only possible value that V can take is 20 meters per second as required. Okay, moving on to the next bit. It says later on the van is moving up a straight road inclined at an angle theta to the horizontal where sine theta is 1 over 15. At the instant when the speed of the van is v meters per second, the resistance to the motion of the van from the non-gravitational forces is modelled as a force of magnitude 200 plus v squared. So that's the same as before. The engine of the van is now working at a constant rate of 15 kilowatts. Part B, find the acceleration of the van at the instant when v is equal to 10. Right, so I've taken the bits of information from what I just read out here, and I now have a diagram represent what's going on. I guess the only thing I haven't got yet is that sine theta is equal to 1 over 15. Now I don't need to use a triangle for this because the only component that I need of the weight is going to be this bit, which is the gravitational resistance to motion, the 750 g sine theta. So I don't need this component because I don't need a normal reaction, and normally I'd use a normal reaction when I've got a frictional force given as mu r. Now this time the forces aren't balanced because we're told that the van is accelerating. So P over V is going to be the tractive force. So P over V is pulling. We've got two forces, the a gravitational resistance, so that's the 750 G sine theta, and also this constant resistive force here, 200 plus V squared, so we need to subtract 200 plus V squared. So that's our resultant force, and that's going to equal to MA, so 750A. Right, let's start to fill in some numbers. So the power is 15 kilowatts, so that's 15,000 divided by V, so it's moving at a velocity of 10. I guess I could have put that on my diagram as well. V is equal to 10 minus 750 G times by sine theta. Now sine theta we're told is 1 over 15, so times by 1 over 15, and then minus 200, and then also minus V squared, which is going to be 10 squared. And I guess if I just divide all of that by 750, I'll get A, because I could probably type all of this on my calculator in one go. Right, if we do that, the top part here actually becomes 710. So I'll get A is equal to 710 over 750. Now that gives us 0.946 recurring, and we want to give our answer to either 2 or 3 significant figures. I'll stick with 3 significant figures. So acceleration is 0.947 meters per second squared. Now you could also give your answer as 0.95 because of the use of G in this question, and round to 2 significant figures, but that's the only time you would round to 2 significant figures is if you've used G in your working. Otherwise, 3 significant figures would be the normal way that you give your answer. Question 2. One end of a light elastic string of natural length L and modulus of elasticity 3/4 mg is attached to a particle of mass m. The other end of the string is attached to a fixed point A on a rough inclined plane. The plane is inclined at an angle alpha to the horizontal, where tan alpha equals 5 over 12. Initially, the particle is held at point B on the plane where AB is equal to 2L, and B lies below A on the line of greatest slope through A as shown in figure 1. So it's all here in this diagram. The particle is released from rest at B and first comes to instantaneous rest at point C, where C is between A and B and AC is 8 over 5L. Find the coefficient of friction between the particle and the plane. Okay, now to answer this question I'm going to be using energy, so potential energy, kinetic energy and elastic potential energy. So I've marked on here the position of C. So I know this may not necessarily be to scale, but it's definitely not to scale. So the distance between A and C is 8 over 5L. The distance between B and C then will be 2 over 5L because the distance between A and B is 2 over L. This is going to help me to work out maybe extension of the string when I get to the second part. So I'm going to start by looking at the energy that I have at the start. Now the way that I do these questions, now I've changed the way that I do these questions. So I'll look at the energy at the start, so start energy. I look at the energy at the end, so N energy, which we'll work out in a moment. And these are going to be different because we have a rough plane. Okay, it says a rough inclined plane. So we lose energy, and the energy that we lose is going to be work done against friction. And that's the only energy that we ever lose in these types of questions. So the energy at the start, subtract the work done against friction, will give me the energy at the end. So I'm starting here with the energy at the start, so I'm going to be doing this part here. So what I'm going to do is I'm going to take where it was initially at the bottom as the point of 0 potential energy, 0 PE. So at the start there is no potential energy, so potential energy is 0. We're told that the particle is released from rest at B, so there's no kinetic energy at the start, so Ke is equal to 0. Now there is elastic potential energy because this string is in tension. Now its natural length is L and it's held at this point 2L, so it's got an extension of L. So elastic potential energy, remember EPE is lambda x squared over 2L. Now we have lambda, that is 3/4 mg, so we've got 3/4 mg times by the extension squared, so that's going to be times by L squared, so L squared, over 2 times by the natural length. The natural length is L, so we'll have 2L. So at the start, this is the only energy we have. We only have basically 3/4 mg L squared over 2L. Now if I simplify that, the L's are going to cancel out, and then or one of the L's will cancel out, and divide by 2, I will get 3/8 mgL. Right, I'm now going to work out the energy at the end. How much energy is there at the end? Now the end basically is at the point C, yeah, the end of what I'm basically considering. At that point, the extension of the string, well, it's at a distance of 8/5L from A. The natural length is L, so that will give me an extension of 3/5 L. So again, let's look at what all the energies are. So let's start with the potential energy. So there was no potential energy before, but now it's moved up, hasn't it? So let's get rid of this line here and probably some of these things here just to simplify the diagram, because we've probably got a lot going on. So we know that the potential energy is mgh, so we've got the mg part already. What's the h? Well, it was at this height at B, and it's now moved up to this height where it's at C, and I can use a bit of trigonometry to work that out. So that length here, that's my h that I want to work out for mgh. Now you'll remember that we were told that it's moved up so that the distance between A and C is 8/5L, which means that this distance is going to be 2 minus 8/5L, and that's 2/5L. So that's like the distance of my hypotenuse in this triangle here. Now, since I've been given the angle, or the tan of the angle, as 5/12, I don't work out the angle. I use a right angle triangle, and I can use this right angle triangle to help me work out this length h here. So we're told that the tan of the angle is 5/12, so opposite over adjacent. That means that this side is 13. So that gives us sine alpha is 5/13, cos alpha is 12/13. This height here is going to be basically 2/5 L sine alpha. Let me write that down first. So h is going to be 2/5 L times by sine alpha. Now, since sine alpha is 5/13, if we multiply the 2/5 and the 5/13, then what we get for the potential energy is 2/13 mgL. Now it comes to instantaneous rest at C, so again there is no kinetic energy, that's 0. And that elastic potential energy is going to be lambda, which is 3/4 mg. The string is still in extension, its natural length is L. At this point its length is 8/5L, so 8/5L minus L is the extension, that needs to be squared, and then we divide by 2 times the natural length, so 2L. Now if we simplify all of that, we will get 27/200 mgL. So the total of all of these things here is going to give me the energy at the end. So I now need to work out how much energy is lost. So what I'm going to do is now start to write this all in one equation. So the energy at the start, total energy at the start, is going to be just 3/8 mgl minus the energy that we lose. Now that's the frictional force, that's going to be mu r, times by the distance that this particle has moved, and that is this distance here, which is 2/5L. So frictional force times the distance it's moved, 2/5L, is equal to the total energy that we have at the end. Now the total energy that we have at the end, unlike the energy that we had at the start, is made up of two parts: potential energy and elastic potential energy. So that's going to be equal to 2/13 mgl plus 27/200 mgl. Now we'll need to work out our normal reaction, so I've added that to my diagram. So I've got the weight mg going down, so the normal reaction is going to equal this component here, and that's going to be mg cos alpha. Cos alpha is 12/13, so when I write my equation again in a minute, I'll write r as 12/13 mg. So let's just put that here, 12/13 mg. Now multiplying the 2/5 by 12/13, we get 24/65. You'll notice every term has got mgl, so that's going to cancel out like this. Now rearranging for mu, I get this calculation here, and that will give me 7/30 for mu. I want to give my answer to 2 or 3 significant figures. I'll go for 3 significant figures. So mu is 0.233, because actually this number here will give you 0.2333 recurring. So yeah, 2 or 3 significant figures for mu, 0.233. I'll just make a note that I've rounded to 3 significant figures. That's always good practice to say what you've rounded to. Question 3. A particle P of mass 3 kg is moving with velocity 2I plus j meters per second when it receives an impulse of magnitude √130 newton seconds. Immediately after receiving the impulse, P is moving with velocity -I plus lambda j meters per second, where lambda is a positive constant. Part A, find I, the impulse, given your answer in terms of I and j. Okay, so I've just taken this information and put it in a diagram. This is by no means meant to be to scale or look like this, but just to give me a rough idea of what's going on. So this particle's changed direction because of this impulse that it's been given. So we're dealing with vectors. Now I prefer to work as column vectors, but I will give my answer in terms of I and j rather than given as a column vector. So impulse is going to be m, and then the vector v minus the vector u, and I know that the size of my impulse is 500, but if I start to fill this in, the impulse is going to be the mass, which is 3 kg. Now v is -1 lambda, and I need to subtract from that u, and u is 2,1. Okay, so as a single term and multiplying by 3 as well, I'll get -9 3 lambda minus 3. Now I know the size of that impulse is equal to the square root of 130. Now I can start actually by squaring both sides. So the size of this, I do Pythagoras. I'm not going to square root it because I'm going to make it equal to 130. So to find the size of the impulse, basically the size of the impulse squared, that's going to be -9 squared plus 3 lambda minus 3 squared is equal to 130. Expanding the brackets and simplifying, I'll get 9 lambda squared minus 18 lambda minus 40 is equal to 0. Solving this on my calculator, I get two values for lambda. One is 10/3 and the other is -4/3. However, you may have noticed here it says that lambda is a positive constant, so that means we can ignore that one. The value of lambda we're going to be using is 10/3. So now I can replace the lambda that I had up here in my impulse, so just highlight that, with 10/3, and now I can work out what the final impulse is now that I know lambda, and that gives me -9/7. I'm going to leave it in the form that they want, so I is equal to -9i plus 7j. So always leave things in the form that they want unless the question doesn't specify. Now, the angle between the direction of motion of P immediately before receiving the impulse and the direction of motion of P immediately after receiving the impulse is theta. Find the value of theta. Okay, so here's my diagram. The easiest way I think of doing it is by using a dot product. Now, when we do the dot product, we want both vectors facing away from the vertex of the angle. So I want to reverse the direction of the 2, 1. I basically want it going this way. So I'm just going to use the negative of that. So -2, -1 in a dot product. So the cosine of the angle is going to be the dot product of those two vectors. So -2, -1 dot -1 10/3, then divided by the size of both of those vectors. So the first one, which is going to be the square root of 1 squared plus 2 squared, so that's going to be the square root of 5 here, and then I want the square root of 1 squared plus basically 100/9, and basically that gives me the square root of 109/9. So the result of this calculation gives us 0.17134 and so on. So if we do the cos inverse of that, we'll get theta is equal to 80.13419 and so on. It doesn't specify, so we're going to round it to 3 significant figures. So theta is equal to 80.1 degrees, and again just write down what we're rounding to 3 significant figures. Question 4. A light elastic string of natural length 8L and modulus of elasticity kmg has its ends attached to 2 points A and B here, where AB is 8L. So distance between these 2 points where the string is attached is 8L, and AB is horizontal. A pebble P of mass M is attached to the midpoint of the string. Okay. The pebble rests in equilibrium at a distance 3L below AB, as shown in figure 2, so at distance 3L there. The pebble is modelled as a particle and air resistance is modelled as negligible. Part A, show that K is equal to 10/3. Now the first thing is to put the forces on my diagram, because this is in equilibrium, so I'll be using forces and balancing them. And I will have the mass of the pebble M and its weight mg going down, and then the tension of this string going up either side here of T. Now, because the pebble is directly below this point here, which is in the middle, then I can put on that the lengths here on both sides are 4L. I'll just put one of them on. Then I can see by Pythagoras, if this is 3L and this 4L, that means that the distance from P to B, and the same on the other side, is 5L. So it's a 3, 4, 5 triangle. So I'll put that measurement on here. Now, to do this question, I'm just going to use the tension on one side because that's half of the full tension. And then once I've worked that tension out, I'll double it to get the full tension that's acting upwards. So I'm just going to be writing down, or the working I'm going to be writing down is for the half string on this side. So for the half string, its natural length is 4L for the half string for this side here. The modulus of elasticity is kmg, and then the extension of this half string, it's currently at a length of 5L, and it was previously 4L, so the extension of the half string is just L. Now here's another picture of the tension here, because I want to know the component of the tension that's acting up here. So I'll put that purple arrow is the one that I want for my working. Now this angle that I'm calling theta here is the same angle that's given on the diagram here. So that's the same angle as the one that I've called theta. Now the sine of that angle here is equal to 3/5, opposite over hypotenuse, and the cosine of the angle is equal to 4/5 adjacent over hypotenuse. Now the component that I want pointing up is going to be then t sine theta. Sine theta is 3/5, so that component is 3/5 t. So now we'll work out the tension, lambda x over L. So lambda is kmg. The extension is just L, and then 2 times the natural length. So remember, I'm just looking at this half string here. Sorry, not 2 times the natural length. I'm thinking of elastic potential energy. Just the natural length, and that natural length here is going to be 4L. Remember the half string. So that's my tension. Now, T sine theta is basically going to be 3/5 of what I've got here. So simplifying that and working out 3/5 of kmgl over 4L gives me 3 kmg L over 20 L, and then you can see that the L's cancel out, so it's just 3 kmg over 20. Now we're going to resolve the forces vertically. They're going to be balanced because it's hanging in equilibrium. So what we've got going down is mg, and that's equal to now 2 lots of these tensions. We're now looking at the full string, so that's basically going to be 2 times 3 kmg over 20. The mg's cancel out, and the 20 and the 2 that cancel out, just leaving you with 10 at the bottom. So we have 1 is equal to 3k over 10, and if we rearrange that, we will get k is equal to 10 over 3 as required. Moving on to part B, the pebble is now pulled vertically downwards from its equilibrium position until the total length of the string is 40 over 3L. The pebble is released from rest. Find the acceleration of P at the instant it is released from rest. Now, just like part A, I'm going to be considering the half string, the tension in the half string. Because it's accelerating, the forces are no longer balanced, it's going to be F equals ma. So just like before, the natural length of the string is still 4Al. Now the modulus of elasticity, we now know the value of K is 10 over 3. So modulus elasticity will be 10 over 3 mg. And then the extension of this half string is going to be half of what it currently is, what it's been stretched to, which is going to be 40 over 6L, minus the length of the half string. So the extension of this half string is 8 over 3L. Now, just like before, we need the component of the tension that's going up. So I've got a little diagram here, and this angle theta is the same as this angle theta. Now the pebble is now pulled further down, so the lengths have changed from before. This is still 4L here, but this length to where the pebble is, this half length here, is going to be 40 over 6L, half of this. So I can work out the cosine of the angle that I want, and that's going to be 4 divided by 40 over 6, and when you do that you actually get 3/5. So that's the cosine of the angle. That means then, well, we don't really need a triangle for this, that the sine of the angle is 4/5. So we're going to do the tension times by 4/5. So tension times by sine theta, that's the component that's going up. And if we work out what that is, that would be lambda. So that's our 10 over 3 mg. So lambda times by the extension, that's 8 over 3L. So lambda x over 2L. Natural length is, and we're talking about the half string here, remember. So the natural length of this half string is going to be 4L, and we're timesing that by sine theta, so we're timesing that by 4/5. So this is, all of that there is the component of the tension going up. Now the L's cancel out here, and multiplying out the rest, we'll get 16 over 9 mg. Now resolving vertically, we've got the two tensions pulling up because the acceleration is going to be upwards, minus the weight of mg is equal to ma. So we have two lots of 16 over 9 mg, so that's going to be 32 over 9 mg, minus mg is equal to ma. Right, what's going to happen? All of the m's cancel out. Then the acceleration is going to be 32 over 9 g minus g, and that gives us the acceleration as 23 over 9 g. Now I wouldn't change this to a decimal to 2 or 3 significant figures because we've got an exact answer in terms of g, which is fine. That doesn't need rounding. Leave it exact in this particular case because it's a multiple of g. Moving on to part C. At the instant the pebble crosses the line AB, which is this line here and this line here on my updated diagram, the pebble has speed v. Find v. Now we're going to be using energy to answer this question. So here's my updated diagram. So this follows on from part B, where the string is connected at these points which are at a distance 8L apart, A and B, and the string has been stretched to a length of 40 over 3L, so each half of the string is a length 40 over 6L. I want to work out the energy at this, what I call the start, the point at which it's released from after being stretched, and I'm going to call this point down at the bottom the point of zero potential energy. So I'm going to work out the energy here at the start. I'm also going to work out the energy here at the end when the string is level with this line AB. And also note that in this question, no energy, not energy, y, but no energy is lost in this question because there is no work done against friction. And the question says that we're ignoring air resistance because it's negligible, it's quite small. So we're going to start by working out the start energy. So how much energy is at the start of this? And that's down here. Well, it's at the bottom. That's the point we're calling 0 PE, so there's no potential energy. KE is released from rest, so there's no potential energy. The only energy we have is elastic potential energy, and that's going to be lambda x squared over 2L. Now remember from the previous part of the question, we've got the modulus of elasticity lambda as 10 over 3 mg. The extension of the string is going to be what it's been stretched to, which is 40 over 3L minus 8L, that's its natural length, and that gives 16 over 3L, that's its natural length. So now we can start putting these values in. So lambda 10 over 3 mg times by the extension squared, so that's 16 over 3L all squared, divided by 2 times the natural length, and the natural length is 8L. Now simplifying all of that, we'll get 160 over 27 mgl. So this forms all of the energy at the start. Okay, no energy is lost, so that's going to be equal to our end energy. And what I mean by end energy is the amount of energy we have when the pebble, or what we're modeling as a particle, reaches this point here. Now the pebble's moved up, so now there is some potential energy going from 0 up to this point, and it's going to be mg and then times by this vertical height here. Now that value of h we can work out using Pythagoras, so that will be 40 over 6 squared minus 4L, this length here, squared, which is what I've got here, and square rooted. We can simplify that. Once we do the calculation, we will get 16 over 3 mgl. Then kinetic energy, so yes, it is moving, and that's half m and v squared, and v is what we're trying to find. And then elastic potential energy, since the string now is level and it's now at its natural length of 8L, there is no elastic potential energy, so that's just going to be 0. So all of this together here forms our end energy. They are going to be equal, no energy is lost, so we have 160 over 27 mgl total energy before, which is just elastic potential energy, is equal to the energy we have at the end. So we've got this gain in potential energy, and we have this kinetic energy, half m v squared. We can cancel out the m's, then rearrange as well, and get v squared is equal to 320 over 27 gl minus 32 over 3 gl. So that simplifies to 32 over 27 gl. So that's what v squared is. And then we want to square root to find v, which we can just leave like this if you just square root the whole thing, or I guess another way, there are various ways of writing it, but another way of writing it is then to work out what the square root of 32 over 27 is. That'll give you 4 root 6 over 9. So another way of writing your answer is 4, and then you've got root 6 and root GL over 9. So various ways of writing answers. As I said, you just could leave it in that very first form. So this is one of those energy questions. Work out the energy before, the energy after, make them equal, solve for the unknown. In this case, it happens to be V. And lastly, part C. In an experiment, when the natural length of the string was 2 meters, it was found that the speed of P at the instant when it crossed the line AB was 1.5 meters per second. D. Considering the model, suggest a reason other than air resistance, because we said that was negligible, or the question said it was negligible, why the model and the experiment give different answers. Okay, I've put a summary of a few things here which I'll try and explain through. So the pebble was modelled as a particle. Well, we might want to consider the dimensions of the pebble. Is it perfectly rounded? Has it got uniform mass? Things like that. Is it small enough for us to model as a particle? Those types of things that might give us different values. The speed was measured as the pebble passed this line AB. How was that done? How was it measured? How can you measure that really accurately? I don't know. Are there machines that do that type of thing? Were they just using a tape measure and a stopwatch to try and measure it? So that would need to be considered. And how was the string connected to the pebble? Was it sort of threaded through like a bead and a hole put through it? Was it just glued to the side? That's going to change the length of the string, make slight inaccuracies. So again, this is something else that may give us different values to what we saw in the real experiment. Question 5. Figure 3 represents the plan view of a horizontal floor where AB and AC represent fixed vertical walls. The direction of AB is in the direction of the vector I. So I'll just put that on my diagram. I for this wall. And the direction of BC is in the direction of the vector negative I plus 3j. Okay, so let's put that on negative I plus 3j. A small ball is projected along the floor towards AB so that immediately before hitting wall AB, the velocity of the ball is 2I minus 3j. The ball hits wall AB and then wall BC. The coefficient of restitution between the ball and wall AB is a half. So let's put that on. E is a half here. The coefficient of restitution between the ball and wall BC is a third. So let's put that here on this wall. E is a third. The velocity of the ball immediately after hitting wall BC is V. Okay, and that's marked here on the diagram. And the floor and the walls are modelled as being smooth. The ball is modelled as a particle. Show that V is equal to negative I plus half j. So we start with the first collision of the ball with the wall AB. We need to work out and find the velocities, the components of the velocities that are parallel and perpendicular to the wall. Now at first it's moving 2I minus 3, so that means 2 across, 3 down. Okay, so this part is 3. The part parallel to the wall is 2. That velocity remains constant after the collision, so it's still 2 here. And then I can use V is equal to EU to work out what this velocity is here, what this part is perpendicular to the wall. So that V is going to equal E, which is a half, times by U, which is 3. So we have 3 over 2. So I can now put in that this part here is 3 over 2. So the velocity of the ball as it's moving towards BC is 2I plus 3 over 2j. Now move on to the second collision. So the ball's moving with this velocity here, 2I 3 over 2. Now I may just use column notation in this next bit rather than I and j, just for saving some space. because to work out these components of the velocity, because the wall's not parallel or horizontal or vertical, I need to use impulse vectors or unit vectors which run parallel and perpendicular to this wall, and I'm going to have to use dot product, and I'll just find it a bit easier to do dot product when I'm dealing with vectors. So we know the direction of the wall. Again, I'll put this as a column vector, so we know that's negative I plus 3. So I'll just write that as negative I, or negative 1 and 3. So I'm going to start with the velocity that's running parallel to the wall, and to find this vector that's running parallel to a wall, I need a unit vector which runs parallel to the wall. So that means I need to divide this vector here by its length. Now its length is going to be the square root of 1 squared plus 3 squared, which is 10. So I want to divide it by root 10. So this is a unit vector that runs parallel to the wall, and I need to do the dot product of that with the incoming velocity, so 3 over 2, and I'm going to get a number from that. That number I multiply by this unit vector here, and it then will give me what this vector is here. So working out this bit here, we'll get negative 2 plus 9 over 2, which is 5 over 2, and we times that by the 1 over root 10, so we'll get 5 over 2 root 10. Then multiplying it out, all of this part at the beginning just becomes a quarter, so we get a quarter negative 1, 3. Now that represents this velocity here, and it represents this velocity because remember the velocity parallel to the line of centers does not change. So I'm actually just going to draw like a bigger version of this out. So I've got this part of the velocity of v, so basically like this bit here, and that is a quarter negative 1 or minus I 3j. Okay, the next bit I want to work out what this part is here. Let me just draw it on. So I've worked out this. I want to work out this part here. So that's going to be this part here. And then once I've got those two vectors, I can just add them up, and that will give me the velocity v. So now I need to look at the velocity which is perpendicular to the wall. Right, so perpendicular to the wall, we need to find a vector which is perpendicular to the wall, which is basically the same direction as the impulse. We haven't got v, so we can't work out the impulse, but there is possibly another way that we could work out what v is. So we know that this direction here is minus 1, 3, so you could think of it as 1 across that way, 3 up that way. So if we rotate that by 90 degrees, we're going to have 3 across and 1 down. So we can have that vector as negative 3 minus 1. So this vector, which is perpendicular to the wall, is negative 3, negative 1. Now we want the unit vector of that, so we need to divide it by its length. Now that is the same length as the previous one, root 10, so we just divide by root 10. Now if we do the dot product of that unit vector with the incoming velocity, we'll get a value of negative 15 over 2 root 10. Multiplying this number with the unit vector, which is perpendicular to the wall, that gives us 3/4 negative 3, negative 1. Now that is this velocity here, the incoming velocity. We need to times that by e 1/3 to get the outgoing velocity. Now remember, e doesn't care about direction, so we need to take the positive of that velocity and times it by 1/3. However, we'll lose the fact that it changes direction, so we'll just times it by 1/3 and that will give us 1/4, -3, -1. So that now gives us this vector here, which is going to be 1/4, -3, -1. Now V is just going to be these two vectors added together, and I've got the calculation down here. So we will get -1/4 minus 3/4 gives us -1, and then 3/4 minus 1/4, that gives us +1/2. So you can see that that gives us the vector -I plus 1/2j as required. Question 6. A particle P of mass 4m is moving along a straight line on a smooth horizontal plane. A particle Q of mass 3m is at rest on the plane on the same straight line. Particle P collides directly with particle Q. Immediately before the collision, the speed of P is ku, where k is a constant. Immediately after the collision, the speed of P is u, and the speed of Q is 3u/2. The coefficient of restitution between P and Q is E. Part A, Part 1, show that there is only one possible value of K. Now the first thing we need to do is to write down or draw a diagram from the given information. That's what I've done here. Now I've left this part blank, and I'm going to explain why and what we need to do here. So this is at rest. P is coming up towards it, it collides. There's only one direction which Q can go in, and that is moving off in the same direction that P was moving in my diagram, off to the right. However, P could continue moving in the direction it was going before, or as a result of the collision, it could reverse direction. So it could be one of those two cases. So its value will be u, but depending on which one I take, it's either going to be a positive u or a negative u. So let's start by considering the case that P continues in the same direction. I'm going to be taking to the right as positive, and I'll start with my equation for the conservation of linear momentum. So that will give me this equation, 4kmu, momentum from P. There will be no momentum from Q because it's at rest. And then after the collision, 4mu from P, and then 9mu/2 for Q. Now, mu's are all going to cancel out because every term has got mu. Then that will give me 4k is equal to 4 plus 9/2. So I can find a value of k, and that is going to be 17/8. Now we're going to move on and use the coefficient of restitution. E is equal to EU. So that will give us the speed of separation. Now they're going in the same direction, so that'll be 3u/2 minus u, it's going in the same direction, is equal to EKU. Now we've just worked out that the value of k is 17/8. Now we can cancel out all of the u's, and then we'll get E is equal to 1/2. That's what we get when we do 3/2u minus 1u, half u divided by u, divided by 17/8. So remember, we've cancelled the u's out. 17/8 is k. That gives us a value of E as 4/17. Now that's reasonable. We can have this value of E is between 0 and 1. So yes, that does mean that k could be a possible value. Now we're going to follow through and do the same thing, but this time we are going to be looking at when we consider P going in the other direction. So I'll highlight it here, and then we're going to see what happens here. Is there going to be some sort of issue if we take P as moving in the opposite direction? So this time when we do CLM, the CLM for P after the collision will now be -4mu, because we're looking at a different direction. So just like the previous time, all of the mu's cancel out. give me 4k is equal to -4 plus 9 over 2. Working that out, that will give us a value of k is equal to 1/8. We'll now put this into our equation for coefficient restitution. This time I'll just use E is equal to V over U, because I had to rearrange it last time anyway. So E is going to be equal to that speed of separation. Now, because P is now going in this way, to find that speed of separation, I need to do 3 over 2U plus U, not minus like before, and then divide that by the speed of approach. So that's going to be the same as it was before, which is KU. Now, I'll get 3 over 2U plus U over KU. The U's cancel out, leaving me with 5 over 2 divided by my value of K, which is 1/8. Now that gives me a value of E, which is 20. Now we know this is not possible, as the value of E can only be between 0 and 1. So I'll just put here, since E can only take values between 0 and 1, including 0 and 1, K cannot be an eighth, because if it was, you get E equal to 20. So K, it can only be 17 over 8. So in the second part of part state the value of K and the value of E. Well, we'll just take the values got here. We just need to state it. We've already worked it out. K is equal to 17 over 8, and E is equal to 4 over 17. Part B, find the total kinetic energy lost in the collision between P and Q. So we'll start by looking at the total kinetic energy before the collision, and that's only going to be kinetic energy that we get from P, because Q is at rest. So that will be half m, and its mass is 4m, times by its velocity before the collision squared. Now we have K, so we know it's Ku, so that K is 17 over 8. So we'll have 17 over 8U all squared. If we multiply that out, we'll get 289 over 32 mu squared joules. So now we'll look at the kinetic energy after the collision. So there's going to be some kinetic energy from both of them, P and Q. So that will be what we get from P, which is half mu squared, because its velocity is u, and then from Q, half 3m times by its velocity 3 over 2 all squared. So if we work that all out, we'll get 43 over 8 mu squared joules. So for the Ke lost, we just look at the Ke before, which is the 289 over 32 mu squared, and we subtract what we have after, which is 43 over 8 mu squared, and that will give us 117 over 32 mu squared joules as the amount of kinetic energy that's lost in the collision. Question 7. Two smooth uniform spheres A and B are moving with speeds u and 2u respectively on a smooth horizontal surface. Sphere A has mass 3m and radius 2a. Sphere B has mass 2m and radius 2a also. The centres of the spheres are moving towards each other on parallel paths. The paths are at a distance 3a apart, as shown in figure 4, this diagram here. The spheres collide. The coefficient of restitution between A and B is 1/3. Part A showed that the magnitude of the impulse received by A in a collision is 6√7 over 5 mu. So I've started off with a diagram here at the moment they collide. So at the point of collision just before, I want to know what their velocities are. So I can see that A was moving across this way with u, B in the opposite direction with 2u, and at the moment of impact, the vertical distance between these, the centre of the two spheres, is 3a. Remember, the radius of each one is 2a, so this distance between the centres going through the line of centres, that will be actually a distance of 4a, which is going to be useful in a moment. Now, with any collision with spheres, we need to look at the components of the velocity which is in line or parallel to the line of centres and perpendicular to the line of centres. That means I need to find out the components of this u velocity and the components of the u velocity. Now, we've not been given vectors, so this is going to be in terms of sine and cos. So I want an angle. So if I put an angle here and call this theta, this angle down here is also theta. Hopefully you can see them because these are alternate angles. And then I can use this 3 and this distance here of 4 to work out what these angles are in terms of sine and cos. So this right angle triangle that I've drawn here represents this triangle here. So here's the 4a, the 2 radii, the 2a and the 2a to make 4a, and the 3a, this distance, vertical distance between the line of centres, these two, or the centres of the circle. So these two red dots represent the two centres of the circle. So I can then use Pythagoras to work out the length of this side in terms of a. So that will be the square root of 4a squared, 4a all squared minus 3a all squared, or 16a squared minus 9a squared. That will give you 7a squared. So the square root of that is going to be root 7a. So then the sine of that angle, theta, is going to be 3a over 4a. The a's cancel out, and so we get 3/4. And then the cosine of that angle is going to be root 7a over 4a. Again, the a's cancel out, giving us root 7 over 4. So now I can work out the components of these velocities here. So I've just drawn them out separately. So if we start with particle A, this part here is going to be u cos theta. Now we've got cos theta is root 7 over 4. So this will be root 7 over 4 u. And then the component that's perpendicular to the line of centres, that will be u sine theta, u sine theta, so that'll be 3/4 u. And then we'll do the same for B, and so this component here that's in line with the line of centres, that will be 2u cos theta, so that will be root 7 over 4 times by 2. So that will become root 7 over 2u. So that is 2u cos theta. And then this component over here, that's this green arrow, that will be 2u sine theta. Then 2 times by 3/4, that will be 3 over 2. So we have 3 over 2u. So now we look at what's going on after the collision. Now remember, the velocities which are perpendicular to the line of centres don't change. So I've left those in green. So they're still going to be like the 3 over 2u and the 3/4 u. However, the velocities which are parallel to the line of centres, they change direction. So I've made them go in the opposite direction. I don't know what these are. So I've called the velocity of A parallel to the line of centres V, and the velocity of B parallel to the line of centres after the collision W. So now I'm going to be looking at the conservation of linear momentum. Now I'm going to be taking this direction down here as positive. So that's sort of going down and to the right, down and to the right. That's my positive. So if we start with the momentum of A before the collision, so that'll be 3m times by its velocity here, which is root 7 over 4u. Then the momentum of B before the collision, now this is going in the opposite direction of my positive, so it's going to be negative. And again, it's its mass 2m times by its velocity, which is root 7 over 2u. And then after the collision, it will be negative 3mv, because that's going the opposite to my positive, plus 2mw. So m's will cancel out, and then if we simplify it, multiply by negative 1, we'll get 3v minus 2w is equal to root 7 over 4u. So now we'll move on to the coefficient of restitution. So v, that's going to be the speed of separation. Well, I've got them going in opposite directions here, so that's going to be v plus w. We're told that the value of e, coefficient of restitution between the spheres, is a third. Now the speed of approach, that's going to be these two added together, which happens to be these two here. So that will be root 7 over 4u plus root 7 over 2u. So it's just these velocities here added. Then that equation becomes v plus w is equal to root 7 over 4u. Now what I want to do is to solve these two simultaneously to allow me to work out impulse. So the way I'll be able to do that is if this is particle A, like this, with a mass of 3m, and the impulse is going to be going in this direction here. So I'll need to know the velocities before and after the collision. So that'll be this one down here. Before, this one up here, like my u in the impulse, is this one here. So it's root 7 over 4u. But what I don't have at the moment is this one, and this is v. So this is why I want to solve these two equations simultaneously to find v, and then I can use that to work out the impulse. So I'll take this second equation and make w the subject, so I can eliminate it from the first one. So w is root 7 over 4u minus v. If I substitute that into the first equation, I'll get 3v minus, and then it's going to be 2 times by root 7 over 4 minus v is equal to root 7 over 4u. So I will get 3v from here, and then 2v from expanding out those brackets. I'll get 5v. Then on the other side, I will get root 7 over 4u plus 2 root 7 over 4u. And you'll notice that I missed out a u here and here, so I'll put those in. And that gives a value of v as 3 root 7 over 20u. So now I can work out my impulse. So I'm taking this direction here as positive. So that's going to equal to the mass, which is 3m. So I'm actually working out the impulse on A. You could also work out the impulse on B. And then it's going to be my v, which is going to be the speed after, which I've just worked out here. So that'll be 3 root 7 over 20u. And then minus the velocity before. Now this is going the opposite direction to my positive, so minus minus, so plus root 7 over 4u. Then adding these together, times in by 3, gives me an impulse of 6 root 7 over 5 mu. Part B. Find the speed of A immediately after the collision. So we can refer back to part A to help us. So this is going to be what we're going to be using. We have the velocities here. So with the 3/4 u we worked out from before, this one was v, and from part A we worked out v to be 3 root 7 over 20u. So it's just about finding the magnitude or the size of this, which we can do by doing Pythagoras. So we'll take both numbers, we'll square them and square root them. When we do that, that will give us the square root of, let's draw a square root symbol properly, 18 over 25 u squared, and taking a positive square root of that, we get 3 root 2 over 5 u. That's going to be meters per second. So there's our speed of A after the collision. Part C. State how you have used the fact that the spheres are smooth when considering their collision. So there's an important fact here, and that's this. When spheres are modelled as smooth, the impulse acts along the line of centres. So we can use that fact to say that we have used the impulse along the line of centres, which is what we've done, not off the line of centres. We could also talk about the fact that there's no spin or no friction.